Good morning, good afternoon, wherever you are listening from, and welcome to the Circuit Breaker live seminar. The session will be split into two parts, with presentations in the morning and live demonstrations in the afternoon. If you have any questions at any point during this seminar, you can put them in the questions tab on the control panel, and we will try to answer them in the Q&A sessions as part of the presentation. I will now hand over to Marius, who will begin the first session.
Hi, my name is Marius Averitai. I'm application engineer for substation testing and commissioning in Dover, UK. Hello everyone and welcome to today's seminar introducing circuit breaker testing. We will go through circuit breaker fundamentals describing the main parts of a typical circuit breaker, followed by an overview of specific tests required to help keeping these important components of the power system running. And of course, we will look at how Megger will help you in performing testing in the safest and easiest way. As part of the power system, since the beginning of electricity use, the circuit breakers continuously evolved, and as a result, you will find now in service a multitude of different generations with a lot of differences from constructive point of view. We will not go deep into different types of circuit breakers. Different materials as training or webinars which are approaching constructive differences are available on our website, and I would recommend you to have a look on our dedicated webinar page. What we will do is try to keep it as simple as possible, referring to typical components of a circuit breaker, as to be able to understand what testing of a circuit breaker can help us with. From constructive point of view, all circuit breakers have a main contact, which will be isolated from earth, with the circuit breaker chamber insulating the two parts of the system when opened using different insulating media as oil, air, vacuum, or sulfur hexafluoride. Typically, oil and air are used by older generation switchgear, still in use, and with vacuum and SF6 being one of the most popular and, let's say, current technologies. In top of that, recently OEMs started developing and already are implementing environmental friendly replacements to SF6, which even if a very good insulating material, it is proven to be not very ozone friendly. So it is in the future going to be replaced by different materials. Open and close operations are obtained by releasing stored energy, commonly stored in a spring with the diversity of other energy storage methods, compressed air, hydraulic system, magnetic systems, and so on. As a part of the circuit breaker, too, we have the control unit with open and closing coils, electrical and mechanical interlocks, auxiliary contacts. So the main contact, insulating medium, stored energy, usually spring, and the control unit. These are the main components of a circuit breaker, of a typical circuit breaker. And of course, with increase of voltage levels, the physical dimensions are getting to a point where it's not convenient to manufacture and accommodate on-site large circuit breakers with a single break per phase. This is where the adopted solution is usually to connect multiple chambers in series, practically using 2 or 4 or 6 lower rated ones. So the voltage level is a limiting factor for technologies used today in having single break circuit breakers, single break per phase circuit breakers. This increase of complexity, having multiple breaks per phase, is bringing extra challenges with solutions are, for example, grading capacitors implemented in parallel with the main contact to help divide the voltage stress equally. And from a testing point of view, synchronization of opening and closing of multiple breaks per phase becomes critical. We will see later differences in timing is specified in standards and has to be monitored. Up to this point, everything looks theoretically simple, but once more attention is paid to the constructive details of a circuit breaker, a higher complexity of the circuit breaker is revealed. For example, the high voltage contact will usually include at least 2 different parts: a main contact and which is designed to carry high level of load current with a minimum level of losses, which require a very low contact resistance, and an arcing contact which has the job to minimize the level of wear by the electrical arc, designed to withstand a number of short circuit operations. Moving further, looking into the operating mechanism part of the circuit breaker, we realize this is in fact one of the most complex part of the circuit breaker due to the number, quite high number of moving parts during an operation. Sometimes this part of the circuit breakers gets overlooked by some from a maintenance point of view. In the same enclosure, a number of auxiliary contacts are usually found, which are used for multiple functions internally by the circuit breaker as operation interlocks, position indicator for the bay control units, part of the substation interlocking schemes for protection functions. As a result, some of these auxiliary contacts are by design leading or lagging the operation of the main contact, and their proper operation needs to be tested during the maintenance cycle. Now, having an overall look with all this information added a typical circuit breaker, which looks quite simple and robust at the first look, ends to be quite complex part of the power system, and proper consideration must be given of how comprehensive the testing will be done. And we'll continue with looking at why we need to test. A lot of reasons, but just some considerations. Beside normal system switching to energize and de-energize, a circuit breaker has to execute a trip from the protective relay when fault is detected. And we can say is the extended arm of the protection strip contact. As a result, high levels of short circuit current will create unavoidably wear of the arcing contact. And that wear level needs to be monitored. Any breaker failure can cause extensive level of damage of the protected power system, and a failure will lead to tripping larger areas with more customers disconnected. In other words, decreased protection selectivity. Added to that, most circuit breakers are exposed to tough environmental conditions, extreme temperatures, pollution, mechanical stress. For example, when they are installed in heavy industrial environments. And another risk factor is being immobilized in one position, usually close, which cumulated with above environmental factors can lead to sluggish or even seizing of coil latch release assembly. As a result, unfortunately, some circuit breakers will fail. And as the industry is interested in minimizing the failure rates by adapting the maintenance requirements, statistics were performed and was found the highest number of faults were located within the operating mechanism. If you remember, I said operating mechanism has quite a large number of moving parts. 70% of the faults are located within the operating mechanism. The interrupter, around 14%, insulation failure, and issues with the frame foundation. For example, let's say circuit breakers, large circuit breakers installed in earthquake-prone areas can be under a lot of stress, and failure of the frame and foundation will affect the overall functionality of the circuit breaker and can lead to catastrophic failures. But the most important ones are faults within the operating mechanism and the interrupter. And all these statistics and previous arguments point to the need of creating an appropriate testing program for circuit breakers. And it is where available circuit breaker analyzers will have certifying your equipment is in good condition or identify changes in parameters as to prevent failure. As a result, a number of test procedures from very basic to extremely comprehensive were developed and are available. And we try to separate this in three main groups. Let's say a standard group, which are recommended to be performed for all types of circuit breakers. An advanced group, I like to say, will give you diagnostic capabilities to look further in the condition of your circuit breakers. And the special group, which are constructive type dependent. For example, pressure monitoring during the test for air blast breakers, vacuum check for vacuum breakers. So taking the standard group, starting with the most basic type of test, which I presume everybody at least will do, contact resistance or static resistance measurement. It is the most basic test performed on any circuit breaker and gives an immediate indication for the condition of the main contact whilst in closed position, with values measured as low as tens of microohms. It's very easy to perform with a very simple test lead connection, extremely accurate, with most instruments available having resolutions down to 0.1 microohms, and accurate measurements are possible due a four-terminal so-called Kelvin method, where the test current is injecting across the test object, in our case a circuit breaker, as the same method can be used for any low resistance measurement, in fact. And the voltage is measured separately with another two leads. And this type of measurement, as I said, can measure down to 0.1 microns, and all our instruments have 0.2% accuracy, extremely accurate. It is very common on the market to find power utilities testing with low currents, 10 amps, but the standards lately started to request higher currents to be used. So IEC standards require for at least 50 amps to be applied for the test. ANSI standards require at least 100 amps, and some manufacturers will require even in their test procedures even higher currents to be injected, sometimes up to the rated current of the circuit breaker. This is to prevent erroneous high readings due contact contamination, due corrosion, and insulating material between contacts. So at least 50 amps or 100 amps for the ANSI standards is a good figure to remember. As accurate this measurement is, it has the disadvantage: it will not indicate the arcing contact condition, where a different method we will see later, dynamic resistance measurement, is used. Practically is a resistance measurement of the contact whilst operating, closing or opening. And we will see later that gives you a better view of the contact assembly. As I said, very simple, easy to perform. One of the challenges in high voltage is to perform the test in a safe environment. And this can be done with new technologies, where what we call a dual ground method can be applied. The advantage is you can measure the contact resistance of the circuit breakers whilst both sides are grounded. The test object will be grounded on both sides through the test, giving a safer, faster, and easier workflow. This is done by injecting current across the test object, connecting the clamp to measure the current through the earth loop, and the instrument knowing how much current is injecting, how much current flows away through the earth loop. It will perform our correct calculation of the true contact resistance. Of the test of the circuit breaker. We have two different instruments available with dual ground method. Milner 200 or 600, capable to inject up to 200 and 600 amps, and the DLR 100. The main difference between them is Milner is mains powered with the advantage of being capable to inject up to 300 amps continuous, 200 for Milner 200 and 300 for Milner 600. And we have the DLR 100 up to 100 amps, which it can be mains or battery powered with enough energy in the built-in batteries to inject 100 amps for around 20 minutes. So more than enough for days of circuit breaker testing. Both instruments will inject pure DC with down to 0.0 micron resolution. A second type of test, which again very important and is one of the most performed tests, is measuring the operating time of the circuit breaker. Operations when closing, operations when opening. The reference values are type dependent and manufacturer dependent, and this is one of the most common questions we are asked: how fast the circuit breaker should open and close, and the details must be provided by the manufacturer. What is stated in standards is the synchronization between phases, and inside the same phase if multiple breaks per phase are installed. So the close operation has to be synchronized within a fourth of a cycle, phase versus phase, or within a sixth of the cycle for open operations. And again, as I mentioned, for multiple breaks per phase, interrupters inside the same phase, they have to be within an eighth of a cycle. This is quite important for balancing the voltage across interrupters in series, as longer delay will lead to uneven amount of stress for the interrupters inside. So for example, the first interrupter to open will have a higher level of stress, and again the last interrupter to close will be under a lot of stress from arcing point of view. It gets complicated when we have main and resistor contacts hence is challenging for the analyzers to be able to detect when each individual main or resistor contact will close. And of course, we need to monitor the auxiliary contacts which are leading or lagging the main contacts if used by protection and interlock systems. Beside the standard closing, which is a measurement of the elapsed time between energization at rated control voltage of the closed coil in the making of the contacts, arcing contacts, and open, which is more or less the exact opposite, measuring of the elapsed time between the energization at rated control voltage of the trip coil and the instant when the contacts, arcing contacts, separate. Some automated test sequences are performed by circuit breaker analyzers to simulate conditions like closing a circuit breaker with a faulted circuit when a close open operation is tested. This is to demonstrate that the breaker is free to trip even with a closed signal on. The contacts will be closed for a very short time, and the mechanical part of the circuit breaker needs to be completed to be able to open. An open-close operation needs to be performed to simulate a reclose operation on feeder circuits. One of the challenges is for the pulse times to follow breaker specifications for the reclose operation. That needs a flexibility in configuration of your test instrument. And a slightly more complex open-close open operation can be performed to simulate a reclose operation for which the fault has not been cleared. So contact timing is quite challenging, but we do have a number of test instruments from very simple, focused on single break per phase. Eagle, which is one of the most comprehensive analyzers for single breaks per phase on the market. It has a built-in printer and allows PC remote control with CapaWin analysis software. CapaWin, which is the same application used by our advanced range TM17 and 1800, which are part of the same family, TM family. TM1800 has a modular concept. TM1700 can be ordered with a flexible ordering capability, and multiple configurations are available. TM1800, as I said, pushes this flexibility further by having a modular concept where the user can reconfigure his test unit by adding or removing different modules. So you can add more control modules, timing modules, analog transducers, and digital transducers as example. I mentioned CapaWin earlier for Eagle as a remote analysis and control software. The TM1700 and TM1800 have exactly the same software built in as CapaLocal, allowing control and analysis on the unit. Of course, the results are compatible with CapaWin for further analysis on a computer, or CapaWin can remotely control the unit if needed. So I mentioned contact resistance, contact timing. The other basic method is minimum trip voltage, which will verify if the breaker operates at lower voltages, simulating problems with the DC-AC supply, as for example, discharge battery bank or supply circuit issues. Minimum values are advertised by standards as percentage of the rated operating voltage. For example, the circuit breaker must close at 80% of the rated operating voltage, AC or DC. For DC, it must open for voltages as low as 70% and or 85% for AC. It is sometimes called a minimum force energy test, and as a advantage, it can allow you to discover friction or bad lubrication, and in top of checking the timing behavior at lower voltages. B10E is a power supply which can provide AC/DC, a reliable and stable unit, continuously output, variable output between 24 and 250 volts AC or DC. It has separate outputs for the closed coil, trip coil, and spring charging motor voltage, and can do direct triggering for minimum voltage testing. In top of the remote triggering of the analyzer you would use with the B10E. And it will be used in conjunction with the breaker analyzer to increase efficiency in the testing sequence. So, as I said, we've gone through contact resistance, contact timing, a minimum trip voltage, and as standard and performed automatically by our circuit breaker analyzer, we have the coil current, and with the help of transducer, we can measure motion parameters. Regarding coil current, this is somehow an overlooked test parameter, but an automatic monitoring of the coil's current during operation and evaluating the results through comparison with previous or reference measurements is one of the most powerful measurements available in a test analyzer. The test instruments will have control through the control modules of the close and open commands. Whilst initiating the pulse, the control modules in the analyzers will perform measurements of the voltage applied and the current in a dynamic way. And at the end of the test, beside the standard measurements like timing or main and auxiliary contacts, you have available a coil current curve. And what is happening when you apply voltage across a coil, the current curve will show a straight transition whose rate will of rise depends on the coil's electrical characteristic and the supply voltage. When the coil armature, which will actuate the latch on the operating mechanism's energy package, starts to move, the electrical relationship will change during operation, and the coil will drop. And the peak value of the first lower current peak is related to a fully saturated coil current, which this will give you an indication of the spread to the lowest tripping voltage. If the coil were to reach its maximum current before the armature and latch start to move, the breaker would not be tripped. It is important to note the relationship between the two current peaks varies with some parameters, particularly with temperature, and again that applies to the lowest tripping voltage. Measuring the coil currents on a routine basis will detect potential mechanical and electrical problems in actuating coils well in advance of their emergence as actual faults. So what you have on the screen now is let's say a real trip coil current, but to do an analysis, you have to identify some points to be compared, and trying to simplify it a bit. What you need to monitor is the two peak values and the times for the peak values, and the first low peak, which is the buffer time, and the moment when current starts to drop to zero, which is practically the moment when the auxiliary contacts in series with the coil will open. So comparing specific points on the curve will help identify issues with the detail level beyond the total trip value. Looking into evaluation of the curve, let's say we have the black curve as a reference and the blue one as the measured one. By comparing the difference between expected times, we can identify issues like contact bad lubrication of the coil armature, part of the energy release. Practically only the first part of the curve was slowed. The second one, if you look at the curve, the black and the blue ones are identical. Another example is when the first part of the curve is identical and the second part is delayed, points to problems in the link system. So the high energy part of the circuit breaker release was delayed for a reason or another. Another example, when both times are increased, points to a problem in both coil armature and the link system. Or another example, when the lower control voltage or bad wiring leads to a drop of energy applied by the trip coil. So this is very easy to simulate by using a B10E and lowering the voltage during close and open, for example. Performing a test with a B10E at lower voltages will lead, of course, to increase in trip times. An increase in the currents measured at the same voltage points to shorted turns of a coil winding. Even if the coil will do its job, if the current, the peak current will increase, that is most probably due to a shorted number of turns. As test instruments capable to do this coil current analysis, again, Eagle and TM17 and 1800, the instruments we have available, both ranges of instruments, Eagle and TM, will be capable to perform this analysis. Okay. The last standard type of measurement, basic, is contact motion measurements. Why measure this? The high voltage circuit breaker is designed to interrupt short circuit current in a controlled manner. It will put great demand on the mechanical performance of all components in this interrupter chamber, as well as the operating mechanism. It has to operate at a specific speed in order to build up adequate pressure to allow for cooling a stream of air, oil, and gas that is dependent of the type of the circuit breaker, for that stream to extinguish the arc that is generated after the contact separation until the zero crossing. It is important to interrupt the current to prevent a restrike, and this is accomplished by making sure that the contacts move apart far enough from each other before the moving contact has entered in so-called damping zone. So all this information will and to be collected and be used for comparative analysis for trends, from trending analysis in during the life of the circuit breaker, or within the same family of circuit breakers, identical circuit breakers. So during the measurement, a number of parameters are calculated as travel. The travel trace indicates the instantaneous position of the circuit breaker contacts during an operation. This gives important information as total travel, over travel, rebound, under travel, contact wipe or penetration of moving contact, or operating rod position at the time of the close and open, and points to anomalies which are evident from the trace. So as I said, over travel, rebound, stroke, different parts of the curve will allow analysis and measurement of each specific parameter. The speed can be calculated between 2 points on the motion curve. The upper point is defined as a distance in length, degrees, or percentage of movement from the breaker's close or open position, or the contact closure or contact separation point. And the lower point is determined based on the upper point. It can either be a distance below the upper point or a time before the upper point. Usually the time that elapses between these 2 points ranges from 10 to 20 milliseconds, which corresponds to 1 to 2 zero crossovers. The lower point vary as criteria depending on the constructive type of the circuit breaker, and the Kaba beam as a software analyzer allows you to select a different criteria for the second point from a number of options. Acceleration can be calculated from the velocity trace, the same as the speed. The damping, which is a very important parameter to monitor and test, as the stored energy an operating mechanism is using to open and close a circuit breaker is considerable. The powerful mechanical stress can easily damage the breaker and or reduce the breaker's useful life. And damping of opening operation is usually measured as a second speed, but it can also be based on the time that elapses between 2 points just above the breaker position. So to perform motion, of course, you need the circuit breaker analyzers I mentioned earlier. The Eagle TM1700, 1800, and this is where it gets a bit more complicated. A number of transducers and accessories have to be used in conjunction with those analyzers. Analog or digital transducers with different ways to measure the motion. You can have rotary or linear transducers. Of course, you need different ways to install those transducers in a appropriate way to limit the possibility to have any damage during the operation. Hence why a flexible mounting kit is useful. Some circuit breaker manufacturers are implementing transducers as default in their circuit breakers, but that is more or less uncommon. So we had contact resistance, timing, coil analysis, and motion. And we will talk later about dynamic resistance measurement. For now, I think we will need to take a short break. Feel free to spend this time to ask any questions or have a tea or a coffee. So see you in 5 minutes. Hello again. So just to do a short recap of the past, let's say, hour, we gone through the standard types of test methods, test types. So contact resistance or static resistance measurement, contact timing and synchronism, minimum trip voltage, coil current measurements, and an overview of the motion measurements with stroke velocity damping and contact penetration and why that is important to monitor. And for the rest of this morning session, we will go through dynamic resistance measurement as part of the advanced or diagnostic measurements. So as I said, one of the most basic type of test is measuring contact resistance while the circuit breaker is closed. But one of the most basic measurements, contact resistance, even if very accurate, cannot give a full image of the condition of the contact. Hence, dynamic resistance measurement can be used with, and it is a very suitable type of test for diagnostic testing. This is performed by injecting DC current through the breaker and measuring the voltage drop and the current whilst the breaker is operated. A breaker analyzer, or the software on the computer, Cabowin, I mentioned earlier, then calculates and plots the resistance as a function of time. And added to that, if contact measurement is recorded simultaneously, you can read the resistance at each point of the contact, and this method is used for contact diagnosis, and in certain cases it can also be used for measuring times. This is one way, for example, to perform timing tests with both sides of the circuit breaker grounded. The TM1800 as a unit, or 1700, is particularly suitable for dynamic resistance measurement, since the timing channels also measure analog signals directly, those minimizing the number of channels and connections are needed. Why would we want to perform this dynamic resistance measurement? To identify the level of wear of the arcing contacts. As I said, the main contacts are measured. The quality of the main contact is measured with a standard static resistance measurement, but performing a dynamic resistance measurement will allow us to identify the level of wear of the arcing contacts without opening the circuit breaker, which is a huge time saver and more or less reducing the cost of the maintenance. How is this done? By, as I said, by injecting current into the main contact during the operation, measuring voltage across the contact, and performing an analysis at the end of the operation. and we will see step by step what details are recorded and at what stage of the opening process. As I mentioned at the beginning of this seminar, the interrupter is a bit more complex than it looks from the outside. You have two different contacts. You have the main contact, which is designed to have a very low resistance and allow for the load current to pass through the circuit breaker with as minimum losses as possible. And for that requires to have a very low contact resistance. But materials with very low contact resistance will not be very good to deal with an arc during normal operations, opening, closing, or opening during short circuit currents. Hence, you have a second contact called the arcing contact, which is designed to sacrifice itself whilst opening or close it. So you want it or not, that arcing contact will wear slowly, and hence you need to monitor that level of wear. So in a closed operation, the current will flow through the main interrupter. So if it is to look on this diagram, current flowing in, going through the main contact and going out, that is normal. That is the first part of the curve we are recording. So as I said, we are injecting current that will have a stable value at the beginning of the operation when more or less the main contact does not move yet. So consistent current being measured, consistent voltage being measured. So the first part of the operation when the main contact does not open yet, and the only part of the circuit breaker which is moving is the trip coil and the latch mechanism, will be more or less the same readings you will have when you perform a standard contact resistance, a static contact resistance measurement. So just to go back, on red current, on blue voltage, or calculated, sorry, not voltage, we are measuring voltage, and the instrument will calculate the dynamic resistance in blue. And what you have in white, just to show you what stage in the operation we are in, we have the motion curve. So if you look on the timing, we started the analysis at 12 milliseconds, not at 0. Practically between 0 and 12, the curve will be identical with the first part described here. No variation of the current or resistance. When the main contact starts to move, the current value is more or less constant, but whilst the main contact fingers are moving during the operation, the contact resistance will fluctuate due some contamination or some uniformity of the surface due normal wear, and the value will reach a point when we'll have a sudden increase. That sudden increase is the moment of separation the moment of separation of the main contact, where only the arcing contact is left to close the circuit. So what you will see is going to be a slight drop in the current through the contact due to the fact the arcing contact has a higher value than the main contact, and the sudden increase, a spike of the resistance dynamically measured. And that spike is the moment of separation between the main and the arcing contact. And of course, for a duration of time equivalent more or less with the length of the arcing contact, the dynamic resistance measured will vary, but will stay more or less around the same value, higher than the previous one, until the full separation of the circuit, when practically the current drops to zero and the contact resistance value increases to infinite, more or less. And that is the moment when the gas pressure build up in let's say in an SF6 circuit breaker, or oil in an oil circuit breaker, will extinguish the arc. So total separation of the contact. Okay, so if it is to go back to the previous slide, okay, not this. So at the end of the measurement, we will end to have a graphical representation like this, and an analysis can be performed. Practically, the end drop of current will be the same reading as the standard timing measurement. In our case, 26 milliseconds. And the difference between the first spike and the second, 22 to 26, that is 4 milliseconds, for which the arcing contact was in the circuit. So using this value in milliseconds it will allow us to do a comparison between the level of wear of the arcing contact within the same circuit breaker. Let's say compare phase ABC, compare it with similar identical circuit breakers, just to identify which one had a higher level of wear, or compare it with previous measurements of that circuit breaker. So let's say if you have maintenance cycles every 4, 5, 6 years, you can look back in the historical results and see if the arcing contact timing decreased as value, which will point to the level of wear. Now, if during this DRM measurement a motion analysis is performed, and if the motion analysis is properly done to the level, we can calculate the speed of the circuit breaker at the opening operation. Having the time and speed will allow us to calculate the length of the arcing contact in, let's say, millimeters. And that full analysis the calculation of the length of the arcing contact will allow us to compare it with manufacturing data. So keeping it simple, you can have a reference value is in milliseconds, but a full analysis where the DRM will use the motion results can give you a calculation of the arcing contact in millimeters. The advantage of using these methods, even they look a bit challenging, is time saving and cost, because the only other way to check for the wear of the arcing contact is to physically open the circuit breaker and visually check for the condition of the arcing contact. So using a circuit breaker analyzer with this type of testing, dynamic resistance measurement and motion, it is extremely cost saving and time saving. Okay, so and as I mentioned, instruments capable to perform this type of measurement are both Eagle and TM series, 1700, 1800s. Some accessories are needed as an extra. As I said, you need to inject current across the main contacts of the circuit breaker during the operation. And that is done with what we call an SDRM supply, which can provide up to 200 amps on 2 channels from a single box. So practically we are using a smart way to inject current during the operation with a super capacitor based supply, which where the injection of current is triggered by the TM1800 just for a very short time during the operation of the circuit breaker only. As a result, we can inject quite a high value of current from a very light box and quite small as a size. So from one box SDRM 202, you can test a 2 break per phase circuit breaker. Of course, if you have a multiple breaks as 2, 4, 6, you need one box for at least 2 breaks per phase. For 2 breaks per phase. Okay. This method can be used, as I said earlier, not only to perform dynamic resistance measurement, but to do an evaluation of the opening and closing timing on circuit breakers, which require for both sides to be closed. Let's say you would prefer to keep both sides of the circuit breaker, as in this case, grounded. Sorry, I said closed, but grounded, to keep your work area safe. Sometimes a standard test method for timing requires for one side of the circuit breaker at least to be open, which in high voltage environment leads to increase of risk for the instrument to induced over voltages and so on, or for the personnel during the test. The dynamic resistance measurement can be used to perform timing for dual ground methods. This is by monitoring the drop of the current at the end of the opening or closing operation, and practically where the current will decrease during opening or increase during closing will indicate the time for the open and the close operation of that specific phase. As disadvantages for the circuit breakers, which have built-in CTs, usually dead tank circuit breakers, the current will flowing for this test will end to magnetize the CT cores, and that can lead to further issues with the way the protection will measure the currents after the re-energizing, and that can lead to false trips of the circuit. So if you use the dynamic resistance measurement method for contact time, you have to make sure you demagnetize the CTs which were in the circuit. Saying that, we do have a better method to test circuit breakers on dual ground, on dual earth, on circuit breakers with both sides grounded, and that is called dynamic capacitive measurement. And just a second, I need to switch my presentation. So this method is a method patented by Megger and available only from us, where we are looking at the circuit breaker as a capacitor, more or less, part of an RLC circuit, where the main contacts and the grounding loops are monitored during the operation with a high frequency signal. And just a second. So during a test session, usually you'll find the circuit breaker grounded on both sides whilst work is performed, and you would want to keep both sides grounded to keep your equipment and the work area in a safe condition. Using the what we call dynamic capacitive measurement implemented in units like TM1800 or 1700, you can perform the measurement whilst both sides are grounded. So all you need to do is to add the DCM modules connected to via an interface to the standard timing channels. You need to connect your control cables as you would do for a standard timing test, and perform a measurement. with the exception of the DCM module, which is the high frequency part of the system. The rest of the connections and the rest of the analysis is done exactly like a standard timing measurement. So once you learn how to use the instrument, let's say for a standard timing measurement, it becomes very easy to use the DCM method to do a dual ground test. This is when compared with the standard timing testing method where one of the grounds is removed. Why don't you want to remove one of the grounds? Is you induce voltages from adjacent circuits or from parallel circuits if you cannot disconnect, for example, the overhead line for a reason or another. And these induced voltages are a risk for the test instrument. And as I said, for the personnel performing the test. Hence, performing the same measurement with the DCM, it has a clear advantage. That will allow to decrease the time. Let's say for a standard instrument without DCM, you will need to stop operation, stop any test steps you are doing to remove the grounding point on one side of the circuit breaker because of the unsafe condition of the work area. You need to ask everybody to stop what they are doing and whilst you are performing the measurement. The DCM test will allow you to skip these steps, and it keeps everything extremely safe. This test method can be used on outdoor circuit breakers and let's say live tank and dead tank too, and GIS too. Okay. So maybe this looked a bit too simple, but in fact is a bit more complex. We have, as I said at the beginning, a number of webinars focused on each individual test technology, DRM, DCM, dual ground. Feel free to go to our website and watch the specific webinars for each test technology. And in the afternoon, my colleague Bill, one of the practical test session she's going to demonstrate will be a dual ground using the DCM method. For now, if you have any questions, you can, we will look to answer and for the next, let's say, 5 or 10 minutes, and we will give you a break. So.
Okay, Marius, there's a few questions that are coming, if you wouldn't mind answering.
Yes.
Which tests can be done on the maintenance of the breaker, and is it necessary to apply lubricant on the breaker mechanism and spring to ensure safe operating?
I would say we would recommend all the tests we described to be done if possible. I know this is not convenient every time, and each let's say organization, let's say power utility, would have their own define test types they will perform depending on the circuit breaker type or the voltage level. Let's say higher the voltage level, more expensive that circuit breaker is an asset, and probably more time and the resources are allocated for testing. But I would say you will always test for the contact resistance, the static resistance measurement, and the timing. And as I mentioned, with our test instruments, when you do the timing test, you will always have the trip coil characteristic measured, and even with that, you can do a sort of a deeper analysis of the condition of the circuit breaker. So I would say, as always, and as a basic test, contact resistance, timing, and coil current analysis, you have it anyway by default. The motion measurement are always performed by manufacturers. It is one of their standard tests they have to do before the circuit breaker is shipped out, and always is done on very high voltage circuit breakers. Regarding the lubrication, just a second. That is checking the quality of lubrication of the, let's say, the low energy part of the mechanism, latch and so on, is quite important, because this is one of the main reasons of failure in let's say older generation circuit breakers. Because of the lack of maintenance, they end to have that lubricant getting dry and sticky, and worst of all, if a bad type of lubricant is used, that can lead to losing the lubricant properties even faster. So you need to always check with the circuit breaker manufacturer what you need to lubricate and what you don't need to lubricate, and what lubricant to use. A first indication of lubrication issues is, I think I had the curve here, just a second. It is an increase of the time for the latch mechanism to be released. So the coil current analysis will give you immediately an indication of problems like contamination or bad lubrication of the coil armature. And if a result like this is obtained, you can check. You will see probably that lubricant, that oil or Vaseline, whatever is used, instead of having lubricant properties, is going to end to be sticky or even worse, feel solid. Okay.
Okay, thanks, Marius. Yeah. One more for you. What normally causes the trip coil to fail or burn?
Yes. So let's say probably the most common reason is related with the previous answer. So if because of the bad quality of the lubrication or lack of lubrication, you end to have a circuit breaker failing to trip. That means the trip impulse will be kept applied to the coil until the fault will disappear. And usually that happens when a backup protection further up the chain will trip, and that happens let's say after another half second or a second, and or even longer times. And the trip coils are designed to have a quite let's say a high mechanical energy needed to release the latch, but they're not designed to be continuously supplied with voltage. Usually in a normal operation, the amount of time current flows through a trip coil will be no longer than the total trip time of the circuit breaker. So at the end of the operation, the trip coil current is cut off by the auxiliary contact, which is synchronized with the main contact. If you have a circuit breaker failure, it will, let's say, if it is not going to operate, that auxiliary contact will not cut off the trip coil current, which can lead to overheating of the trip coil, and more or less is going to burn. Insulation is going to get deteriorated, and that will lead to short circuits. So I would say beside the failing of, let's say, old age or any other stress, the main source is failure of the circuit breaker to operate when closing or opening operation was needed, because that will lead to an increase of time the coil will be energized, and the trip coils are not designed to operate for a very long time. All right. Anything else?
Okay, thanks, Marius. That does it for the technical questions, but I just wanted to mention, obviously, we've had a few comments about if there's going to be a recording available and the presentation available, and certificates. So just wanted to clarify that you'll receive a recording of this presentation and a certificate of attendance tomorrow morning. So keep an eye out for that in your inbox.
Okay, so we are ready now for a break, if I'm not mistaken. And what time are we going to be back? 12 o'clock?
Yeah, I'd say they start at 12 for the demonstrations.
Okay, so see you guys back at 12 o'clock for the second part of this seminar, where our colleagues from Sweden, Böhl and Yle, will go through 2 different practical demos of the test methods we described earlier. See you later.
Hi and welcome. My name is Boel Ekberg. I'm the application specialist of the circuit breaker in the factory of Mega in Sweden. I'm going to do 2 demos this afternoon. I'm going to start with doing a measurement with our small analyzer, Eagle, and there I'm going to do a normal timing. I'm going to measure also coil current and motion. An hour later, in 1 hour, I'm going to continue to do a measurement with TM800, where I'm going to do dual ground. I'm going to have the circuit breaker grounded on both sides. This, of course, is a bit odd here because my object is here not connected to any switchgear at all. It's, as you can see on a truck, just pulled out. So I have to do sort of a fake grounding here to be able to simulate this. So that technique, I would say, is more for outdoor breakers where the circuit breaker is in connection the whole time. I want to mention before we start also that you of course need to follow all local instructions regarding safety. As you see, and as I said, the circuit breaker here is not connected, so of course it's not really the same situation here. But of course, let's get started. I'm going to, as I said, do the Eagle. I'm going to measure timing, 3 phases, and also auxiliary contact timing on this object. This is a Sachet 12 kV old oil breaker, and not in the best of shape, so it's a bit slow, but it will work for this demo. When I do this test, I also need a B10E, a power supply, because I need to have power supply for the coils and also to charge the motor. So let's get started. On the object here, I have prepared and short circuit one side because this circuit breaker is not grounded since it's in this workshop environment, and the timing leads here have one common point. So I connect this in advance. So the first thing I do is that I'm going to connect the supply for the motor. I'm going to connect to the motor outlet on B10E and to the terminals on the circuit breaker. I need the supply for the coils, the plus and the minus. And what I'm going to do here, I'm going to use the plus to create the pulse. So the plus goes to the analyzer and it will meet the minus on the circuit breaker, on the coil for the circuit breaker. I also need to connect the close and the open. The close on the instrument and the open on the instrument, and close and open on the object. There's no reason to show you any details on the connection on this side because this will be special on any circuit breaker and you will not have the same object. I take a standard cable set for Eagle, connect to the timing. And as I mentioned before, it has the 3 for the 3 phases and a common for the other side. The clamps are big and sturdy. And of course, it's important to connect to the right phase for the red cables. So phase A, B, and C, and I follow that with the cables. Because, of course, if you find a fault, it's important to know which one is the trouble. I also want to measure the auxiliary contacts. Auxiliary contacts, Marius mentioned before, and that is the contacts which are, as you could say, relay or control contacts in the circuit breaker. And the ones we're interested in are the ones which are in the coil circuit. They are the most important ones. They're really important so you don't burn coils, and also, you must make sure that they are following, because they are like a protector of a coil. I connect to the auxiliary outlet and I connect to the circuit breaker. I can also mention that now when I connected the controls, it's important to go via these auxiliary contacts, because as I said, they are the like a safety. And also there is things like spring charging contact in the circuit, so the circuit breaker is prepared to do the operation. So you don't send pulses to the coils when it's not prepared. So I had the controls via the auxiliary contacts, the timing, and the auxiliary contact timing. Now I have one thing left, and that's the motion. The motion is prepared here. Let's see. I have connected a rotary transducer to the mechanism. The transducer has a holder and an arm. And I connect that to the motion outlet of the instrument. This test is going to be done standalone. As Marius explained earlier, you can also do this test with a computer. But as I said, you can also do the test without a computer, like I'm going to do now. So the preparations are made. I also made sure that the pulses are long enough, and I actually turned off the printer and turned on my channel here. What I need to do before I do any operations is that I need to charge the spring motor. So I'll make sure I have it turned on motor. A little bit noise. And I move the voltage back to this outlet. To get voltage out here continuously, which I want now because I want to control on this one, I need to link here and make sure the contact setting is in contact position. And the breaker is open but charged now. So the instrument here indicates that it's not closed, right? And it wants to do a close sequence. So it's going to be a little noise. I have 110 volt and it's on coil. So I'm going to turn the knob and it's going to be a measurement. It needs a little time. And I need to go to the display here. In the main menu, you have a display. The result is that now the breaker is open and the first auxiliary contact is closed. So that is as expected. And if I go down one more step, I can see that the close time was 83 milliseconds. And for L2, it was 82.9 and 83 for L3. So A, B, and C phase are very, very similar, as expected. A difference between at 0.1 milliseconds. The current peak is as low as 102 milliamps, so it is consuming a very small current. The stroke was 99.5 millimeters. I used relative stroke here, so what you can say here is that you have to take this speed and stroke into a little bit consideration, because we just look at this as it is the maximum. You use 100 millimeters as a relative motion, as you want to compare. You have to compare the motion. You can't take this as exact figures. Speed 4.5 milliseconds. Yeah, so probably this breaker has a stroke which is similar to that, 200 as I used. I'm also going to do a printout here of a result. You can have it to automatic printout, but I normally do it like this. It takes a little while, but you will get the printout right. First, it makes an administrative part, and then it gets results, and it also prints out the graphs. While we're waiting, we can check. Yes, the breaker is closed. Another thing we can check is, okay, I said we have communication possibilities. If you want to communicate, you're going to use a USB on this instrument. And the instrument also has the possibility to do this advanced measurement Marius was talking about this last hour, the dynamic resistance measurement, when you use this outlet. So we're going to get the same results, of course, as in the display. But here we're also going to be able to see the graph for coil current and motion. One thing I didn't mention before is that the B10E supplies either from coil or from motor. So you have to switch in between. So the coil current is very, very small, as we mentioned before, and the motion, yeah, it's a normal slope, I would say. We continue with the sequence. I'm going to move back to sequence menu and do an open operation. I go back to the result menu on the display, and the opening time was 55.1, 55.7, and 55.5 milliseconds. So the phase difference was 0.6 milliseconds. And the current for the open is higher by just different coils. So that one is 485 milliamps. And stroke 100, yeah. And speed was 2.9 milliseconds. What you can do is also, of course, measure multiple operations. But of course, now, since this one is not connected the whole time to the supply, I need to charge the motor again. And what are those multiple operations? Yeah, Marius mentioned them before, that you want to simulate different things, like you connect the circuit breaker to a fault, and how quick does it open again. So you can do an operation like a close open. So again, I have to check, I have my supply, and it's going to be a multiple operation now. A little bit noisier, but. And you get the different times, the close and the open, and the difference in similar ways. So by this test, you check that the circuit breaker is quick enough also when you have connected towards a fault. This was what I wanted to show you with Eagle actually. Is there any questions regarding the demonstration? No? So in 45 minutes, we're going to do a test with a TM1800. So then we're not going to do this kind of timing where you only can have one side grounded, but we're going to have both sides grounded, which is, of course, a very safe way to work when you work outside in the switchgear where you have capacitive coupling, induced currents, and this kind of thing. And also, of course, risk of coupling. We have had a few incidents recently in Europe where people have connected the supply to the breaker because there are other persons in the station, or a mistake between different operators which are not used to work together, so they have misunderstandings. So then it's very good to work with both sides grounded, because then you have a protected area where you are working. So if somebody would do a fault like that, the current would go through the grounding leads instead of down to the instrument. Okay, see you in 40 minutes. Thank you for the attention.
which is time-consuming and moreover increases safety risk. When the measurements are done, the ground cable has to be attached again before the measurement cables can be removed. With Megger's dual ground method, the circuit breaker can be timed without removing the ground, which makes the test both safer and faster. With the TM1800 and the dual ground method, you can also time gas-insulated switchgear and generator circuit breakers without removing ground connections. Read more about Megger circuit breaker testing at megger.com. Timing measurements on circuit breakers with both sides grounded. According to international safety standards, a circuit breaker should be grounded on both sides while work is performed. Start by connecting the TM1800 to ground. Connect the DCM cables to the circuit breaker. Connect the control cables to the circuit breaker strip and close coil circuits. The test can now be performed safely. Conventional timing methods would require one ground cable to be removed before measuring, which is time-consuming and moreover increases safety risk. When the measurements are done, the ground cable has to be attached again before the measurement cables can be removed. With Megger's dual ground method, the circuit breaker can be timed without removing the ground, which makes the test both safer and faster. With the TM1800 and the dual ground method, you can also time gas-insulated switchgear and generator circuit breakers without removing ground connections. Read more about Megger circuit breaker testing at megger.com. Timing measurements on circuit breakers with both sides grounded. According to international safety standards, a circuit breaker should be grounded on both sides while work is performed. Start by connecting the TM1800 to ground. Connect the DCM cables to the circuit breaker. Connect the control cables to the circuit breaker strip and close coil circuits. The test can now be performed safely. Conventional timing methods would require one ground cable to be removed before measuring, which is time-consuming and moreover increases safety risk. When the measurements are done, the ground cable has to be attached again before the measurement cables can be removed. With Megger's dual ground method, the circuit breaker can be timed without removing the ground, which makes the test both safer and faster. With the TM1800 and the dual ground method, you can also time gas-insulated switchgear and generator circuit breakers without removing ground connections. Read more about Megger circuit breaker testing at megger.com. Timing measurements on circuit breakers with both sides grounded. According to international safety standards, a circuit breaker should be grounded on both sides while work is performed. Start by connecting the TM1800 to ground. Connect the DCM cables to the circuit breaker. Connect the control cables to the circuit breaker strip and close coil circuits. The test can now be performed safely. Conventional timing methods would require one ground cable to be removed before measuring, which is time-consuming and moreover increases safety risk. When the measurements are done, the ground cable has to be attached again before the measurement cables can be removed. With Megger's dual ground method, the circuit breaker can be timed without removing the ground, which makes the test both safer and faster. With the TM1800 and the dual ground method, you can also time gas-insulated switchgear and generator circuit breakers without removing ground connections. Read more about Megger circuit breaker testing at megger.com. Timing measurement on circuit breakers with both sides grounded. According to international safety standards, a circuit breaker should be grounded on both sides while work is performed. Start by connecting the TM1800 to ground. Connect the DCM cables to the circuit breaker. Connect the control cables to the circuit breaker strip and close coil circuits. The test can now be performed safely. Conventional timing methods would require one ground cable to be removed before measuring, which is time-consuming and moreover increases safety risk. When the measurements are done, the ground cable has to be attached again before the measurement cables can be removed. With Megger's dual ground method, the circuit breaker can be timed without removing the ground, which makes the test both safer and faster. With the TM1800 and the dual ground method, you can also time gas-insulated switchgear and generator circuit breakers without removing ground connections. Read more about Megger circuit breaker testing at megger.com. Timing measurement on circuit breakers with both sides grounded. According to international safety standards, a circuit breaker should be grounded on both sides while work is performed. Start by connecting the TM1800 to ground. Connect the DCM cables to the circuit breaker. Connect the control cables to the circuit breaker strip and close coil circuits. The test can now be performed safely. Conventional timing methods would require one ground cable to be removed before measuring, which is time-consuming and moreover increases safety risk. When the measurements are done, the ground cable has to be attached again before the measurement cables can be removed. With Megger's dual ground method, the circuit breaker can be timed without removing the ground, which makes the test both safer and faster. With the TM1800 and the dual ground method, you can also time gas-insulated switchgear and generator circuit breakers without removing ground connections. Read more about Megger circuit breaker testing at megger.com. Timing measurements on circuit breakers with both sides grounded. According to international safety standards, a circuit breaker should be grounded on both sides while work is performed. Start by connecting the TM1800 to ground. Connect the DCM cables to the circuit breaker. Connect the control cables to the circuit breaker strip and close coil circuits. The test can now be performed safely. Conventional timing methods would require one ground cable to be removed before measuring, which is time-consuming and moreover increases safety risk. When the measurements are done, the ground cable has to be attached again before the measurement cables can be removed. With Megger's dual ground method, the circuit breaker can be timed without removing the ground, which makes the test both safer and faster. With the TM1800 and the dual ground method, you can also time gas-insulated switchgear and generator circuit breakers without removing ground connections. Read more about Megger circuit breaker testing at megger.com. Timing measurements on circuit breakers with both sides grounded. According to international safety standards, a circuit breaker should be grounded on both sides while work is performed. Start by connecting the TM1800 to ground. Connect the DCM cables to the circuit breaker. Connect the control cables to the circuit breaker strip and close coil circuits. The test can now be performed safely. Conventional timing methods would require one ground cable to be removed before measuring, which is time-consuming and moreover increases safety risk. When the measurements are done, the ground cable has to be attached again before the measurement cables can be removed. With Megger's dual ground method, the circuit breaker can be timed without removing the ground, which makes the test both safer and faster. With the TM1800 and the dual ground method, you can also time gas-insulated switchgear and generator circuit breakers without removing ground connections. Read more about Megger circuit breaker testing at megger.com. Timing measurements on circuit breakers with both sides grounded. According to international safety standards, a circuit breaker should be grounded on both sides while work is performed. Start by connecting the TM1800 to ground. Connect the DCM cables to the circuit breaker. Connect the control cables to the circuit breaker strip and close coil circuits. The test can now be performed safely. Conventional timing methods would require one ground cable to be removed before measuring, which is time-consuming and moreover increases safety risk. When the measurements are done, the ground cable has to be attached again before the measurement cables can be removed. With Megger's dual ground method, the circuit breaker can be timed without removing the ground, which makes the test both safer and faster. With the TM1800 and the dual ground method, you can also time gas-insulated switchgear and generator circuit breakers without removing ground connections. Read more about Megger circuit breaker testing at megger.com. Timing measurements on circuit breakers with both sides grounded. According to international safety standards, a circuit breaker should be grounded on both sides while work is performed. Start by connecting the TM1800 to ground. Connect the DCM cables to the circuit breaker. Connect the control cables to the circuit breaker strip and close coil circuits. The test can now be performed safely. Conventional timing methods would require one ground cable to be removed before measuring, which is time-consuming and moreover increases safety risk. When the measurements are done, the ground cable has to be attached again before the measurement cables can be removed. With Megger's dual ground method, the circuit breaker can be timed without removing the ground, which makes the test both safer and faster. With the TM1800 and the dual ground method, you can also time gas-insulated switchgear and generator circuit breakers without removing ground connections. Read more about Megger circuit breaker testing at megger.com. Timing measurements on circuit breakers with both sides grounded. According to international safety standards, a circuit breaker should be grounded on both sides while work is performed. Start by connecting the TM1800 to ground. Connect the DCM cables to the circuit breaker. Connect the control cables to the circuit breaker strip and close coil circuits. The test can now be performed safely. Conventional timing methods would require one ground cable to be removed before measuring, which is time-consuming and moreover increases safety risk. When the measurements are done, the ground cable has to be attached again before the measurement cables can be removed. With Megger's dual ground method, the circuit breaker can be timed without removing the ground, which makes the test both safer and faster. With the TM1800 and the dual ground method, you can also time gas-insulated switchgear and generator circuit breakers without removing ground connections. Read more about Megger circuit breaker testing at megger.com. Timing measurements on circuit breakers with both sides grounded. According to international safety standards, a circuit breaker should be grounded on both sides while work is performed. Start by connecting the TM1800 to ground. Connect the DCM cables to the circuit breaker. Connect the control cables to the circuit breaker strip and close coil circuits. The test can now be performed safely. Conventional timing methods would require one ground cable to be removed before measuring, which is time-consuming and moreover increases safety risk. When the measurements are done, the ground cable has to be attached again before the measurement cables can be removed. With Megger's dual ground method, the circuit breaker can be timed without removing the ground, which makes the test both safer and faster. With the TM1800 and the dual ground method, you can also time gas-insulated switchgear and generator circuit breakers without removing ground connections. Read more about Megger circuit breaker testing at megger.com. Timing measurements on circuit breakers with both sides grounded. According to international safety standards, a circuit breaker should be grounded on both sides while work is performed. Start by connecting the TM1800 to ground. Connect the DCM cables to the circuit breaker.
Are we back? Welcome back. The demonstration with TM1800 will not start just now, but I thought I would take the opportunity to talk a little more about this dual ground technique. Some tip and advice when you do this in the real situation. There are, I would say, two situations normally you use dual ground. It's either outside on an outdoor circuit breaker, distribution, transmission, or on a GIS, either in inside or outside, right? When you do this dual ground timing on an outdoor breaker, it is important that you use grounding equipment which are separate per phase. There are types of grounding devices which has what do we call it? 3 parts, 1 to each phase. And you could use it, but then you have to use it on only one side. If you use this kind of common grounding unit on both sides, you will get into trouble. The system needs a proper grounding loop for each phase. But yes, you can do common grounding on one side. I was doing a demo in Spain a few years ago where we had this kind of situation where we only had this kind of grounding device. And what we did was that we used ferrites to separate the grounds instead. So we put ferrites on the grounding device. So that was one way of overcoming it. Another important thing to know is that you should always connect at the breakings, at the pole. When people hear, oh, dual ground, oh, then I can connect at ground. Yeah, if you're experienced, maybe you will manage this because you know how to put the grounds. But for any normal user, and especially, of course, for beginners, always connect close to the break point. That's really, really recommended. Ferrite, what is that? Yeah, that is like an inductor you can snap on the grounding device. And when we mention that, it's very natural to go over to these gas-insulated switchgears. Sometimes you have real trouble measuring those on normal timing, because they are you can't ground them separately, and also the only place where you have access is to the grounding points commonly. So again, but then we have a common ground part. What do we do then? Yeah, again, we're using these ferrites to separate the groundings. ABB, for example, they have commonly a star ground point, and you can put the ferrites over that star and actually connect directly on each side of a ferrite. That sounds really strange, but it works. And also, I've been around where we measured on the GIS, where we have no connection points at all inside the switchgear room. So we had to go outside and connect up on the slacks on the bushings in the house. So the bushing out to the lines. There we connected, we grounded outside, connected there, and connected to like grounding in the structure. And also we were down also in Spain, actually, where we had a transformer directly connecting on the output. So there was a cable directly from the GIS, and there was no access point, and we connected up at the transformer on the flanks of the transformer, and the grounding of a cable connected to the transformer. So there could be different ways of accessing this. But okay, when you do this kind of thing, there are this commonly works very, very well, and you get exactly the same result in the software. So you have a normal timing trace, and if you have troubles with getting it to tune, you have to look for if there are any extra groundings. What do I mean with extra groundings? Yeah, again, ABB as an example. We've seen this on other types as well. But in that housing where the grounding is, they have a heater, and that heater is on a plate. And commonly that one is short-circuiting the ground between this star and the common point. So then you have to make sure you don't have a connection with this plate. This kind of issues can occur. It's not very common, but it exists. But otherwise, when you do this, it's really, really easy to use. Instead of normal timing leads, use a box like this, and the whole measurement is done with resonance frequency instead of what we did with Eagle before, just a voltage and checking if there is a connection or not. So for the user, it's quite the same, especially on the outdoor breakers. It's as simple as a normal measurement. And of course, much, much safer. That's what we developed this for. We wanted to be able to follow the regulations where it says you should keep the two sides grounded to work on the object. This kind of timings, which we did with Eagle, has been done since, I think, 70s at least, where we came with a product which is called TM1600, which is still out there, but we don't sell it anymore. That's using the same principle as Eagle. And TM1800 and TM1700 can also do this kind of timing. And actually that channel used is also used during the dual ground timing as the measurement reader. But to do the dual ground timing, you need an extra module. If you see in the window here, it shows the configuration of this specific instrument, and this has control and control, double controls. Why? We have controls for close and for open, because we want to be able to control separately if we want to do that. We have a normal timing module, and we have this dual ground timing module. So these two modules work together during this measurement. Then we have an analog module, which is used for things like motion, but also for dynamic resistance measurement. And you can use it for other analog values as well, like voltage, current, motor current, for example, these kind of things. We have auxiliary contact timing, and we have a digital channel, incremental channel. We can read incremental transducers, motion transducers, if we don't want to use the analog channels. So you have quite a big possibility with this setup. But if for this breaker, of course, I don't need this big configuration. I would manage with one control module. So in this way, you can adapt your instrument for what you've been doing. In a few minutes, we will start the presentation again. So this was my little extra device pause session, influenced by, we got fed up by hearing the small video. And at English time, 1 o'clock, we will start the real demo. Has there come up any questions regarding this? Ulla, do you have any questions? Do you see any questions?
Yes, there's some question about the ferrites, the
ferrites, yeah.
meters. Maybe you can clarify a bit about them, why you have them and what they are, and if they're included with the instrument.
DCM is a module, so it's not always included. And the ferrites are not always included, because normally you don't need them on the outdoor breakers. So it's like an accessory for the dual ground on the GIS. But sometimes in extreme cases, you could use them also on normal outdoor objects. But preferably I would use a separate grounding device, as I recommended in the beginning. But they are metal, metal units which have a very high inductive material, which influence the resistance. It's not the resistance, it influences the whole inductance of the circuit through ground. So we put them over the ground, right, to change, not the resistance actually, but to change the circuit to ground. You could also use like a longer grounding, but in a GIS, the reason why the ground, the resistance is not enough is that the whole pipe is grounded. So the pipe is working as part of the ground. So the resistance in the pipe can be lower than what you're trying to measure inside. So when you do like a resistance measurement, and that also influences if you try to do a timing result. So that's why we also here have to use this to alter the inductance in the grounding circuit. I think it's just sharp now, so I think I'm going to start with introducing myself again, because some of you might not have been part of the whole session. We just had a short extra session about dual ground while waiting for this demo to start. And 1 hour ago, I did a demo with traditional, I would say, normal timing. We just tested the circuit breaker in a traditional way by supplying voltage over the phase and checking when we have a circuit. In some, we recommend to do this in another way, but then you need this bigger instrument to use something called dual ground timing. Another name of it is DCM. We call the module DCM. Normally you look at the circuit breaker as a resistance, but during this measurement, the instrument looks at as it was a capacitance instead. And we do a resonance frequency. I have prepared my setup here. I have grounded all phases on both sides. I even kept the ground. It doesn't really matter, actually. I can have one side common like this. I'm going to do timing with dual ground, and then I need to use this type of cable instead of a normal timing. So it has a little box. And I think I weighed this equipment once, and it was 900 grams, I think, and the normal cable is 600 grams, I think. So it's not much heavier and not very trouble to connect or anything. So what I'm going to do now is to start connecting the controls. And I'm going to measure, just like before, timing, coil current, and motion. With both Eagle and TM, both 17 and 1800, the coil current is measured automatically by the control circuit. So when the instrument is controlling, it's also measuring the coil current. But the motion needs to be connected separately to an analog channel. So let's get started to connect again. I need again to connect the motor. To my object. I need to get minus to the object and plus to my instrument. I also need to link here because I'm using different channels here. So I need to link. So I get supply for both close and open. Since I also want to measure the voltage, which I didn't mention, but I want to measure the voltage too, I need to connect the minus also up here. But I'm going to use now the control cable set. One side, a shorter split. And I want to connect the minus I mentioned. To be able to measure the voltage. I want to connect also the close and the open command. You can't see what I'm doing here in detail. So if you want to see that, I recommend you to go later to our videos on mega.com, where you can see in detail the connection work. That it's much more complicated camera work than to be able to do live. And close and trip to the object. With TM 1800 and TM 1700, the auxiliary contacts in the circuit of the breaker is measured automatically by the control module. So the control module here is more advanced than with Eagle. So I don't need to do the connections for that. But I need to prepare to do the dual ground. And what I need to do that is to connect one extra cable. It's a very odd one. It looks like this. That's a link between two modules. We don't want to lock the module MR module to only be able to do DCM, dual ground, but we want it to be flexible. So instead we use a cable. I connect the phase A As you see, it has quite a long split. I used this on an 800 kV breaker, and the split was long enough. But if you need a longer split, you need to have a special cable for that. I connect over phase A, but I make sure to have a little bit of loop. Outside, this is not a problem, because if you have a big distribution or transmission breaker, this gap will occur automatically. But since this is more tight, I do a little bit of a gap. I don't put them like this, I put them apart. So this is commonly not a problem. Phase 2. And as you see, it's also long cables. So for this 800 kV, we did expand, but not the gap, right? So we expand the part which was common. Again here, keep them a little bit apart. It twisted itself a little bit here. Probably this cable is a bit newer than the other one. That's why it's twisting like this. I can, let's see. Also avoid crossing these two faces with the cables. And the last phase, phase 3. I can go the other way around to keep it separated. And motion. I connect to analog channel, analog cable, to the prepared motion connection. One thing I forgot to mention before, which can be good to mention, is that you must make sure that things are not coming into the mechanism here. And especially when you mount your motion transducer, that it should not interfere with the mechanism of the circuit breaker. And if you're using a linear transducer, that you know which way the link arm is going, so you don't damage the transducer. Because if it tries to move outside region, the physical impact can damage the transducer. But commonly we try to use the rotary ones because they are quite, they fit on very many objects, I would say. Again here, I prepared a setup. And if you want to look at details on doing the setups, also there, we have videos on the, as I said, on the, both on YouTube and on mega.com, where you can see the details. Before I start measuring, I need to do one more thing. I go to find my breaker and I create a new test. And I need to tune the breaker, tune the setup. The instrument needs to know how the circuit is as a reference. And to do that, the circuit breaker needs to be closed. So the first thing I'm going to do, I'm going to start the motor, I'm going to close the breaker, and after that, we can tune it. So I'm going to start and close it. And the instrument has the possibility, so I can actually just say I want to close it. Without measuring, by turning it up instead of down. It's going to be a bang again. So now the breaker is closed. Now I can tune it. Let's see if I can show you that it's flashing here. I don't know if you're going to see it. I'm going to try to show you in this mirror. Do you see the mirror now? You don't know. I will see. Because the instrument starts flashing. Do we see the flash? Maybe. But it's flashing all 6 channels, and it gets to a steady light when it's tuned. So now it's prepared. So after this, you shouldn't move the cables. They are now tuned to this position. And I can do the open operation. So I'm going to start measuring by turning the knob. And that's going to be a bang. You notice it has a bar here before it starts. So if you, for some reason, don't want to be close to the circuit breaker when you operate it, you can set that timing to a longer time, like 120 seconds or something, right? And what we can see here on the screen is now the timings, red, yellow, and blue. The auxiliary contact timing, the light blue ones, and the coil current, and up here is the motion. And I can read out the result, 55.5, 56, and 56. Yeah, quite similar as Eagle, of course, because it's measuring the same thing. I need to charge again. And now it's prepared to do close operation. We'll do that. And it has auto sequence here, so I don't have to do anything normally. It jumps to the next operation automatically. It's going to be a bang again. For some reason, it didn't manage to read the auxiliary contact. That was interesting. Okay. We get the timings for the 3 phases, for 1 auxiliary contact, coil current, and the motion for the close. I don't know why it didn't manage to read that auxiliary contact. I know it's quite a noisy contact, so maybe that was because of that. Yeah. Has there occurred any questions? Because that was what I was planning to show you.
So, one question is, any polarity should be followed for the control cables which attach to poles? So,
These cables doesn't have any direction, no. So when you measure a breaker with more breakpoints, then you actually normally would use 2 clamps per breakpoint. When you measure classical timing, the cable has 3 parts. So then you have to consider which one is the common part, which is the midpoint of a T or Y on the circuit breaker.
How do I perform dynamic resistance measurement? Can I do it with the same setup, or?
You can prepare the setup like this, but you need to disconnect here. And you need a box, a current injector box. It's our box, our injector box is called SDRM, because we use it for static and dynamic resistance measurements. And it's a box this size. I'm sorry, I didn't bring it. I could have brought it. I didn't think about that. This big box, which weighs less than 2 kilos. But of course, the cables also have a weight, but it's a really convenient box. This box replaces a battery of 15 kilos plus, I would say, and the injector controller, which was the same weight as this box. And our box actually has 2 channels. So if you measure on an outdoor breaker with 2 breakpoints, you measure both points at the same time. It's a really convenient little box, about this big.
Can I perform that test at the same time while I perform the dual ground timing, or should it be 2 separate?
It is 2 separate measurements, but you can connect everything at the top from the beginning and just have it disconnected. There is, again, a video on YouTube explaining also this, actually, how to do it, and also these different connection possibilities.
Also, you was very clear that the cables needed to be separated. What would happen if that wasn't the case?
The risk is that it doesn't tune here. Should we try it? How much should we try it? Because if I twist them, for sure it won't work. That I know. But I always need to be closed when there's a risk of less good performance, you could say, right?
So you get the timing wrong, or what happens?
No, it will not tune, or you will get no result, proper result. It's not twisted now, but they're quite close to each other, and the breaker is closed. So I can try to tune it again. It would be funny if I don't manage to get it to not tune, because sometimes it works even better than I expected to do. So it looks like it's tuned, but to see, we put it into monitor, and it shows that it's closed. So I open it. I can do the measurement, of course. That's better, right? But the risk is that it doesn't manage to handle it, right? So I do an open operation. Again, it's going to be a noise. Oh, it managed anyway. So now I stand here telling you should be careful, and you don't even need to be careful. They are very tight now. But I have seen occasions where it has been too tight. And the problem can be also when we deliver these cables, they are even twisted like this, right? And that's not a good idea. But as I said, as soon as you come outside, this is not a problem at all, because you have big distance, right? It's just totally different situation. And also it depends on how good grounding situation you have. Maybe I have a good grounding here. So I didn't manage to make that happen. Let's see if I close it again. Gonna be bang again. I'm a bit surprised there with the readings in it. Oh, yeah, here we actually see it didn't manage with the phase B. So we can also get out here and watch the monitor in the view here. As you see, phase B is now indicated not closed. And if I play around with these cables, I could get it to change actually. So that's a bit odd as well. Right? So don't move these cables main changes. If it falls down, I would recommend you to retune. But as soon as everything is up and outside, it's not trouble to think about even. Was there any more questions? No?
No, I think from our side, we're done with the
And UK, are there any more leftover questions? Can you write to Ulle maybe?
I don't think there's any more questions. I think Marius has answered some questions live in the chat, so I think he's done that. So so no, if there are no more questions at the moment, but if you do have some, please feel free to put them in the chat and we will get back to you privately. Please don't forget the recording of this session and the certificate of attendance will be in your inbox tomorrow. So keep an eye out for that. But thank you for attending and keep an eye out for the next seminar coming soon. Thank you.
Thank you.